Okay. Um, Hello, everybody. Welcome to this uh, extra session of the seminar. It's my pleasure to present you Erdal, who is my collaborator, but also a very good friend. We met a long time ago doing the postdoc in Germany. And now we are very good friends and very good collaborators.
Time flies.
He's here for 2 weeks, so 1 week already happened, and next week he will be still here. I will use also this time to promote that we have a meeting of China, Mexico in the Institute of Physics next week. So please also go there. You will know a lot about the Chinese way to do science and how to do collaboration with them, which could be great for you. Probably Erdal will tell you some of that at the end or at the beginning, don't know. He's in the Institute of Physics of the Chinese Academy of Science. He was before that in Tel Aviv, and before that he was in University of with Torquato, but I don't know. Princeton. And before that he was, that was the postdoc time, Tel Aviv and Princeton. Before that he did his PhD in Düsseldorf, where we meet, and that's it. So he's a very curious guy for my point of view, because he was born in Turkey, moved to Germany. When he was in Germany, he was more German than Turkey, and now that he's in China, he becomes a bit more Chinese than German, and the German part is forgot. And when he's here, he's more Mexican than me. So.
Yeah. In fact, people talk to me in Spanish when we are together.
Yeah, that's happened. So I hope you will enjoy this talk about hyperuniformity glasses. I don't know if you know what is hyperuniformity, but I discovered with him. He's the expert. And I just love it. So now I am very inside this stuff. So please give.
Thank you.
Welcome to.
Gracias,
Thank you.
Gracias. Thank you very much.
Please begin.
I'm really quite happy here. It's my second time, by the way. I came last year, January, over a year ago, again for a collaborative project with Atta. And every time I come here, I enjoy it. The only problem is it's too far from me, so it's really 20 plus hours flight. So I wish I could be here more often, but we will see. Maybe in the future, flying time will be shorter. So we know each other from quite a long time, over 10 years, and recently, a couple of years ago, we started collaborating. We have published already our first paper a couple of years ago. And then we are continuing actually our project. But our project is on quasicrystals. Atta and I work on quasicrystals. He actually somehow, motivated me to work on quasicrystals. So as I motivated him to work on hyperuniformity. So it is quite a nice, a genuine collaboration going on here. So I'm very happy to be here, and I hope I can come more often. And I hope to see you at some point. Please, if you have any plans to come to visit Beijing or China, stop by in the Institute of Physics. And we hope that in the future we can basically strengthen our ties between IOP and UNAM. Well, when I mean IOP of Beijing, not IOP of UNAM. Institute of Physics. Right, so today I'm going to talk about actually a project I'm currently working on. It's not finished yet. So I would appreciate more even your comments. So it is on glasses, which is completely new field to me. So this is my first project on glasses. It's a bit challenging at the moment, but I'm learning a lot, and I'm investigating the problem of, let's say, glass transition from a completely different perspective, namely from the lens of hyperuniformity. And we believe we have observed and we still observing quite interesting phenomena in the glass physics. Just looking through the lens of hyperuniformity, it teaches us a lot of things. All right, so the talk is about how liquids undergo a crossover or transition into glassy state. this is the classical picture. You have a liquid, you cool down the system. If you do it rapidly enough, you can omit crystallization, you end up in a glassy state. And you know, there's a huge debate going on, what about this glass transition, whether it exists or not, and then there's this other temperature, Kaufman temperature. So I'm not going to talk about all these details, but what I'm going to show you today is, hopefully, that if I start cooling down the system, not from an ordinary liquid, but from a hyperuniform liquid, the glass phase I get in this region is not the same, or they have quite distinct structural and perhaps also dynamical properties than the ordinary glasses cooled down from ordinary liquids. Now, in a minute, I will come back to what ordinary is and what hyperuniform is, and I will explain to you more in detail what I mean by specifically hyperuniform systems, including hyperuniform liquids. So I was told that there will be a few students here, and hence I have prepared rather an extensive introduction to hyperuniformity. If you are familiar with it, it might get a bit boring, sorry about that. But I will try to make it as compact as possible, at the same time as, you know, broad as possible, so you understand the basic concepts of hyperuniformity. Formally, we can define hyperuniform systems as those where the long wavelength density fluctuations are anomalously suppressed. Okay, what does it mean? Let's make it a bit more visual. Imagine I have a set of points. These could be, you know, people, could be chairs, tables, molecules, planets in the galaxy, whatever. And then I'm going to take an observation window, a sampling window, for instance, a square one, a circular one, okay, of a certain radius r. And I'm going to just, you know, count the number of elements, let's say particles, inside this window. So it's very simple, right? And then I just take the same circle and put it on different places. I sample basically my sample. And I keep counting the number of particles. And then what I'm going to do is I'm going to calculate the fluctuations in the number of particles contained in this circular sampling window. Basically, I'm going to calculate the standard deviation, or the square of it, basically, the number variance, okay? The variance associated with the number of particles inside these observation windows of radius r. This doesn't have to be circular, this can have different shapes, but for simplicity, we take circle. Or, you know, hypersphere in any dimension. Basically, what I'm showing here, and the remainder of the talk is about 2D. Well, that's a system where I put all these points, the particles, randomly, without any correlation. The other end of the spectrum is obviously a highly ordered state. Let's take a crystal. And I do the same calculation, okay? I do the same game, basically. Now, what I realize, if I calculate the sigma square, the number variance, is that the number variance in a system where I just put these particles randomly grows actually with n, which is proportional to the volume, or this area of the circle. So when I put a window and I keep changing the position of the window and I calculate the number variance, the variance grows. I'm not talking here about the coefficient, I'm talking about the proportionality, right? The variance grows as r to the power dimension of the system d, in this case 2. On the other hand, since this is more regular, and when I keep moving my window here, all the change comes basically from the circumference of the sphere. So it grows with r to the power d minus 1, dimension minus 1, in this case linearly in r. So we say that the system is uniform and that system is hyperuniform. It grows faster than the dimension d in r. So to quantify this further, so this is the real space picture I was just mentioning. whenever the number variance associated with the number of particles inside an observation window of dimension r, whenever this grows slower than the area, in this case it grows as r to the power 1, but in principle it can take any exponent beta. Whenever this beta is smaller than the dimension of the system, we say the system is hyperuniform. This can be translated directly into the real space. What we need to do is to look at the Fourier transform, the structure factor, which is the density correlation in the Fourier space, which is basically the Fourier transformation of the pair correlation function. It's a two-particle correlations in K space, in Fourier space. And in fact, there is a mathematical rigorous relation between sigma and structure factor S. And this condition is fulfilled only then if the structure factor goes to 0 as the wave number goes to 0. I will show you a few examples in a minute. So, as you can imagine, in many contexts, it is better to look at the structure factor because, especially experimentally, if you do some, atomic molecular experiments, you don't really know where your atoms or molecules are. So what you do is scattering experiments, and then you measure, the scattering intensity or the structure factor. Then you can tell something about the system, right? So of course, if you work with colloidal systems, for instance, then you can simply easily track the particles, the colloids, and you can also measure the real space, the sigma square. Now, these typically, not always, but typically the structure factor scales as a power law in K with a power law exponent alpha. Again, not always, but in equilibrium systems, almost always. There are exceptions, but these are more marginal cases. So this alpha, the exponent of the scaling in structure factor, and the exponent of the scaling of the number variance are related to each other. Now, I'm not asking you to memorize this. After so many years, I can't still memorize myself. The only difference is, well, what you have to memorize here, or what you have to pay attention, is that there are different classes to as to how the scaling of the structure factor or the scaling of the hyperuniformity behaves. These three different classes have distinct scaling properties and also somehow distinct physical properties, sometimes, not always, but sometimes. So if in 2 dimensions, for instance, your number variance scales as r to the power 1, like the crystal case, then we say it's a class 1, and that's the strongest form of hyperuniformity. That's the strongest form of systems, the class of systems where the fluctuations are suppressed most strongly. I mean, you cannot get lower than r to the power 1. So that's basically a lower bound. You cannot have an exponent in 2 dimensions which goes r to power something smaller than 1. And then the weakest form of hyperuniformity is what we say class 3. That is where alpha is smaller than 1, and hence in 2 dimensions the beta is somewhere between 1 and 2. So it scales. The fluctuations are less than the volume of the sphere or circle, but higher than the circumference. So it's in between ordered, like crystals, and random structure, which lacks completely order. And there is a marginal case with a logarithmic correction. This happens sometimes, but I would say more rarely. So this gentleman, Salvatore Torquato, where I also spent part of my postdoc, is the guy who actually pushes this field. But I must also say that actually before he published this paper, the preliminary paper in 2003, some other people called these systems super homogeneous. So this concept is actually known. for a very long time. In fact, from the classical liquid theories from the 70s, some people know that if you take, for example, long-range interactions, there is like electrolyte solutions, etc. The structure factor goes to 0 as k goes to 0. This is known. This was known for a long time. However, Salvatore kind of created. He did a lot of important research, and he made this as a long-standing field because he worked a lot on physical properties of these systems. So he investigated quite a lot, put a lot of effort in the last 20 years from different perspectives in different systems, in quantum systems, in classical systems, in biology. So it is now, I would say, a well-established subfield of statistical physics, the research on hyperuniformity. So there's a very nice review, which is already quite old actually, 2018. It is very mathematical, but it is, I would say, complete back then for 2018. And since then, there are at least 2 reviews I'm aware of. One is more on material properties. The other one is more on the non-equilibrium systems like active matter and viruses and bacteria or active models that can also have hyperuniform character. So, and this field keeps growing at the moment. I don't know how long, or it is a growing field. So there are at least 2 more reviews I'm aware of since 2018, and perhaps even more. Okay, so let me give you a couple of examples for hyperuniform systems. So you can, classify or categorize in your mind what is hyperuniformity and what's not hyperuniformity, just by specific particular examples. I will focus actually on this slide, at least on the structure factor I mentioned. You will remember hyperuniformity condition is that your structure factor goes to 0 as the wave number k approaches goes to 0. Of course, at k equals 0, it's never 0, right? Because it's the forward scattering, but we don't take this into account. Typically, ordered phases of matter, such as crystals and also quasicrystals, are hyperuniform. So whenever you have a diffraction pattern, well, actually, in case of quasicrystals, it's more complicated, but in case of crystals, you have these Bragg peaks, and we say this is basically a gap, right? The first Bragg peak is given by the 2 pi over the unit, the lattice constant, it is 0, right? So in case of quasicrystals, it's a bit more complicated, but it also decays to 0 except one case we recently saw an article of, which is quite an interesting phenomena, which, okay, is very, very mathematical, but as far as we know, we can say with certainty that almost all quasicrystals decay to, the structure factor of decay to 0. They're also hyperuniform. So that's the hyperuniformity, let's say, closet. So hyperuniformity means basically whenever you have order in the system, long-range order in some sense, can be translational symmetric order, can be also rotational symmetric order, can be any type of order, then the structure factor, the system is going to be hyperuniform. Whereas, on the contrary, if you have non-ordered, let's say, disordered systems, phases or states of matter, such as liquids, or ideal gas, or gases, or glasses, for that matter, typically structure factor does not go to 0. And also keep in mind that the limit value of k to 0, S of k, is related also to the isothermal incompressibility. So it has also a thermodynamic relevance in equilibrium systems. So yet there is recently a lot of research going on systems that are disordered but still hyperuniform. And that's the interesting part of all that story, in my opinion. So, obviously there are a lot of systems that are, disordered and hyperuniform. We are not the first one. There's at least 10, 15 years of research on, colloidal suspensions, random jammed packings, even, biological photoreceptors in chicken's eye, more mathematical systems, for instance, the non-trivial zeros of the Riemann zeta function, etc., etc. So these systems are kind of intermediate in that sense, that they look like liquids or disordered systems. There is no long-range positional correlation, yet they suppress density fluctuations just like crystals and quasicrystals do. And that's the interesting part of the story. So here are just a few examples. I haven't updated my slide. This is, I think, from a couple of years ago. There is, just to give you a flavor of, there are colloidal suspensions, there are mathematical models, this Mana model or critical absorbing states. The photoreceptor cells in the chicken's eye, Riemann zeta zeros, bacteria swimming at the interface, air, liquid, circulating, etc. They are all hyperuniform. So there's a huge research going on. Some of them have also interesting physical properties in the sense that they are useful material properties. I usually don't talk about this part because, my interest is more fundamental, not necessarily trying to find an application, but some people have worked on applications of hyperuniform systems. For instance, photonic band gaps. I mean, this is quite crazy because typically people thought the band gaps can occur only in crystalline materials. But turns out when you are hyperuniform and disordered, somehow there is some short-range order which is mimicking the crystalline short-range order. But you can open the band gaps, at least in the photonic region. So, or you can create stealthy materials. This is inverse. Okay, what you do is you assume a structure factor which has 0 up to a certain value and then some form. And then from that structure factor, you inverse engineer a point pattern. Now this point pattern is transparent to incident light below this K. So, there are some, of course, patents about this. And yeah, so there are some optical properties that might have potential use for these hyperuniform systems. But as I said, my interest is mainly in the fundamentals of these hyperuniform systems. Now I'm applying this whole box of hyperuniformity to the glasses, okay? But maybe before I continue with my real talk now, with my research, is there any question on hyperuniformity so far? And also please, just interrupt me in the middle, so just feel free to say, stop, I don't understand, or whatever. So if there are any questions on hyperuniformity, on that concept I just introduced, also later, please, of course, you can anytime ask, interrupt me. Okay, so coming back to that picture. So taking a non-hyperuniform liquid, cooling it down, avoiding crystallization, getting into the glassy regime has been studied to the death. So, I mean, there are really tens of thousands of articles, and if there are 10,000 physicists working on glass physics, and there are 10 million theories about this, it's a huge field, and there's a lot of interesting research by very smart people going on. So I'm not really going to touch this. But this is something quite phenomenal we just came up with. It's very interesting. We have a hyperuniform liquid, and then we try to get glasses. And it turns out that these glasses are actually have some different, distinct properties from other glasses people study so far. So the first part of my talk has been published last year, so December 2024, over 1 year ago, which is the high temperature region, hyperuniform liquids. And the second part is ongoing work. What happens if I take these liquids or fluids and I cool it down and I get glasses, which we call Wigner glasses because they are purely stabilized by repulsion. There is no attraction. Okay, so, yeah.
Liquids are normally not hyperuniform?
Normally, no.
So how
Water is not hyperuniform, for example.
Okay,
Yeah.
so how can you get hyperuniform liquids?
By doing this.
Okay.
By basically assuming a long-range interaction. By assuming a liquid where the constituent elements, like, okay, I'm doing, classical physics. I assume pair interaction, of course. I omit any higher many-body interactions. What I do is, in the simplest case, in this, okay, so give me a second. Okay, so how do I get hyperuniformity in the liquids? It's very simple. This is also known, by the way. This is nothing new. You may ask, why did you publish if it's known? Because when we use long-range interactions, we just discovered something people hasn't seen. Okay, so we assume a pairwise interaction with a repulsive power law, 1 over r to power s. Now, this power s can be any power, but this power s is usually smaller than the dimension of the system, and I will show you in a second. So this is the Fourier space representation of the interaction potential V of r. Okay, we make a little trick. We write a functional for the entropy. We use this form, which is valid in the mean field region at high temperatures where you can neglect actually many body effects. But it turns out it works also very well for lower temperatures. Anyway, this has been published a few years ago by our colleagues. Okay, so what we do is we write a functional for the free energy. This is an excess entropy and excess free energy. What that means is that's the difference from your system at a given temperature to the ideal gas. And the excess free energy is U minus TH, TS, or we don't call it S, we call it H. And then we minimize this excess free energy, and then we get this form of the structure factor. Well, because we know what U is. U is the internal energy, which is given V in K-space times structure factor. Again, this is all valid in the high temperature in the mean field limit. So this gives us a very simple form for the structure factor. And now, well, there's a lambda, which is like a characteristic length, which is written like this. Alpha is D minus S. D is the dimension, S is the exponent of the long-range interaction. And it is very easy to see here, but you have to do the math, that if S is smaller than the dimension, then the structure factor goes to 0. Otherwise, the structure factor goes to a constant. So if you are in 2 dimensions, and you take 1 over r, or 1 over r to 0.1.5, then you are hyperuniform. So, but this was known from the 70s. That's nothing new about it. So, but the interesting part is that lambda acts as a screening length if S is smaller than D, because it grows with growing temperature, with increasing temperature. But if S crosses, that should be the other way around, larger than D, then it is like a correlation length. Basically, this length increases with decreasing temperature. Anyway, so here is your question, answer to your question. If you use a power law potential, repulsive power law, and if you take an exponent which is smaller than the dimension, in 2D, for example, if you take 1, it is hyperuniform. Otherwise, it is not hyperuniform. If you take 1 over r cubed, it's like a dipolar interaction, or r6 and r12 is like Leonard-Jones, they are not hyperuniform. Well, and then we did some theory, and it actually agrees very well for smaller S's, but also for larger S's, it agrees very well as the temperature goes up. This is the temperature. So, but this was known. We just reinvented the wheel because, so we did this functional, and then we minimized the energy. We got this, which was known from 50 years ago. We just reinvented the wheel. But we saw something else, which is quite interesting. So this is a bit now tricky part, so I don't want to talk much about this part, but I want to mention the main concepts in this part as well. This guy here, the entropy diverges if S is larger than D half. But entropy cannot diverge. In reality, it doesn't diverge as well in the simulations and the experiments. But the theory says it diverges. So what's the problem? By introducing an upper cutoff in K-space, we realized that this divergence comes from the large K limit. So from short length scale correlations. But since it cannot, so you would assume, that when you have, let's say V of R, the pair potential. This one is, let's say, 1.5. This one is the S. S is 1.5. And this one corresponds to S 0.5, for example. So if your S, as your S increases, your short range, the energy you're paying off is larger. So you would expect that this actually would lead to stronger correlation. But stronger correlation, we just realized from our functional, actually causes a problem. The entropy diverges, so it cannot be. So what we realize is that, in fact, in order to avoid this, the system decorrelates particles at short length scales. That means there's a stronger, faster approach to Poissonian at short length scales. Only then, well, this is 1 minus S, that means for larger S, 1.5, the system pushes the particles closer to 1, faster. Sorry, the structure, the correlations faster to 1, so faster to Poissonian. It is stronger. The correlations towards Poissonian are stronger than for smaller S, less than d half. Otherwise, the entropy diverges. So I know it's a bit confusing, but the main point here is that there is another transition we have actually found that, like a crossover exponent, where you are all over hyperuniform in this region, but if you are less than d half, you just have small k fluctuations dominating. If you are between d half and d half, your short wavelength, large k fluctuations are suppressed more strongly. And this has, on the other hand, so I mean, you might say, fine, well, so what? But this has some thermodynamic consequences, namely the specific heat, or the density, the potential energy, the fluctuations in the energy through the calculation of the specific heat is different in the two cases, okay? So if S is smaller than d half, basically, if your short range correlations energy doesn't factor in so strongly, as you increase your temperature, the energy fluctuations kind of, they saturate, they don't care much about. So no matter how high, how strongly the particles are fluctuating and oscillating, your energy fluctuations basically stays constant. But it's not the case for an exponent larger than d half because of the stronger short range decorrelation, we call it. Stronger, higher short range energy so because for S larger than d half, the total energy is larger, so this larger energy basically causes the system decorrelate faster. So, and then it really still cares about temperature. It still keeps going up the energy fluctuations. So this is something which we believe has an effect also for other phenomena. We haven't analyzed that yet, but since whenever you have fluctuations, in this case we have looked at the potential energy fluctuations, by the way. We don't, you take into account only the potential energy here. For instance, currently we work on clusters, microphase separating systems, where you have also fluctuations of the cluster size and fluctuations of the energy depending on the thermodynamic parameters. And it seems like this difference also, this distinction is also somehow giving rise to different phenomena in other systems. So, okay, I know it's a bit confusing. What I'm trying to say here is that there is a qualitative difference whether your S is larger or smaller than d half. Now, I'm taking this system, I'm cooling it down to get a glass, okay? And this is partially also with the student Huang Jiuyuan from the lab of Xu Limei at Peking University. Okay, so going back to your question, we have long-range interactions, so the liquid is hyperuniform, or the fluid, because in this case we can't really distinguish between gas and liquid because there's only repulsion. But in order to, okay, so one way to create a glass is to quench it very quickly, but in the computer, no matter how quickly you quench, you always get a crystalline lattice if you don't have disorder. Now what we are going to do is we are introducing disorder in the V0, in the interaction amplitude. So we are basically sampling the interaction amplitude from a uniform distribution around the V node. And we are now assigning pairwise interaction amplitudes. So each particle pair has a different interaction amplitude now. The width of this distribution is given by delta. If delta is too small, if the interaction amplitudes differ only slightly, as I will show, you still end up in a crystal. Only if these interaction amplitudes are large enough, you end up in a non-crystalline amorphous state. You may wonder why we chose this weird Vij. There are some technicalities. Instead of taking energy per particle pair, I could also take Vi per particle. But then, since I'm doing swapping, it happens that particles, they are close, the energies Vi's and J's, they are close to each other. They would like to stay closer, so you get polycrystalline system. So in order to not run into this technical problem, I'm using these Vij. So if there are n particles, there are n times n minus 1/2 values of Vij, pairwise. Okay, so this is the pair interaction, pair distribution, pair correlation function, G of R, for a specific value of S. So at high temperatures, it's just, there's almost no structure, and then the most blue one is the zero temperature, frozen one, basically. You have these liquid-like shell structure at zero temperature. And then we also measured size 6, the bond orientation autoparameter, at high T, and we go all the way to 0T. And well, without disorder, you have a phase transition to crystal. With disorder, not much happens. Or maybe something happens, but we can't resolve what's happening here. So we can't say where is the glass transition here. Not yet. So come back to delta, to the width of the distribution. Okay, if the distribution is 0, you end up in a crystal, obviously. If your distribution is still small, you have also still crystals, I would say, with some grain boundaries, and you keep losing this. Okay. And you get the highest disorder in some sense for the largest delta you have, which is 1, by that construction. Now, it depends a lot on how you anneal the system, etc. So, because you also, at some point, you don't equilibrate anymore. You have to wait very long to equilibrate. And when you're below the TG, you have to wait infinitely long to equilibrate, but it doesn't happen, obviously. So these technical details depend on annealing rate, etc., etc. But overall, the picture is, as delta increases, your disorder increases, also measured by G of R. The highest delta has almost no structure and almost no fluctuations. The lowest delta corresponds to the lowest delta 0 corresponds to Bragg peaks, but delta equals 0.2 and 0.4. There are basically frozen systems with some defects, grain boundaries in it. Now the question here is, we know that this is hyperuniform, okay? And we freeze all the way to 0 temperature. Does it stay hyperuniform or not? So is hyperuniformity still conserved by the glass transition? Well, I wouldn't ask this question if it wasn't, right? The answer is yes. This is the structure factor, okay, versus the wave number k. This is a log-log scale, even though that looks like it's not hyperuniform, but it goes down very slowly to 0. And as the temperature is decreased, you're suppressing more and more the fluctuations. And interestingly, these fluctuations even survive glass transition. They are even becoming more hyperuniform, measured by alpha. I will show you in a minute. quite interesting. So you have a liquid which you cool down, and you end up in a system which cannot anymore equilibrate, which we call glass, by that definition, dynamic definition. And this glass is also hyperuniform. And I will show you in a second that this glass is different from the liquid from which it forms. So it is in a way like a glass, like a phase transition. I mean, yeah, not a thermodynamic phase transition in the classical sense. We don't, there's no symmetry breaking, etc. But in a way, the liquid is different. The glass is different from the liquid from which it forms, which is against the main, main idea of glass. There has been studies that have showed, okay, the glass has not 2-point, but if you go to higher 3-point and 4-point correlations, you see some differences in glasses than in liquids, obviously. But even at the 2-point level, I think this is the first study that shows that there are clear structural distinction between glass and liquid. Because the classical, the dominant idea is that glass is a frozen liquid. We believe it's not that simple in this specific category of systems. So these are I'm sorry. So hopefully it still works. Yeah, it does. Perfect. So this, otherwise I owe you a laser pointer. This gives us actually a phase diagram which is completely hyperuniform. This is also something new. Usually hyperuniformity occurs at just a single point in the phase diagram or so. Well, I mean, the liquid, as we know now, is hyperuniform. The crystal is hyperuniform trivially, and these, well, it's not phase diagram, but like a state diagram from liquid to glass happens to be also hyperuniform. So this gives you basically a state diagram where everything is hyperuniform. Now you can start talking about maybe, well, can I have some hyperuniformity thermodynamics, since I have already the entire phase space hyperuniform? What happens at these, transitions? We can start asking these questions now. For now, in the first part of the talk, I've shown you this region, and now I'm showing you this region. Now I have disorder. This is supposed to be delta, not epsilon. Yeah, so, and then now I'm going along this line. I'm fixing the disorder, and I'm decreasing the temperature towards 0. For different system sizes, yes. So now I'm measuring here alpha, which is here, the scaling exponent, versus temperature. We know from this, what I've shown you in the first part, that if I use this S, 1.5, mean field limit is D minus S, namely 0.5. And we are going there, we are approaching there for very large T. But then this exponent alpha keeps changing as you change structure, the temperature, as you decrease temperature, as you anneal, this alpha keeps changing. And there are 2 bars I put here, and now in a minute I will tell you what these bars mean, these vertical bars. All right, so what we do here is we measure the correlations in the orientational relaxation, size 6, as a function of time, and we measure its correlation. And we see that these correlations diverge at this temperature, which we call Tg. But that is indicative of that once you reach this Tg, what's happening here is you go from one class to another class of hyperuniformity. Yeah, so you're crossing this one line. This also holds for a different S, by the way, not only for this S. So this is obviously more clean for larger number of particles. It all depends on the system size, etc. But this part doesn't depend much on it. So you cross from class 3 to class 1 hyperuniformity, to strong hyperuniformity, as you cross this line, Tg, the temperature. Well, you may ask, okay, well, this is only the orientational relaxation, but we have also looked at the intermediate scattering function, the self part of it, which measures the positional correlations of particles, not their orientational, but the positional. Like you keep track of the particle at at 0 time, and then you keep track of it, and then you measure the correlations, and it turns out that it coincides. Actually, that's the classical way how we define a relaxation time, how people find what a glass transition temperature means, typically, and so if you wait longer, we don't know what will happen, but we believe it will go up. It will diverge. But so that's the critical point. So we cannot say at the moment it is a glass temperature, but we say that at least within our simulation time, these guys stop equilibrating. And this you can do for different modes. It doesn't matter. So what happens here is basically you are crossing into a glassy region where things don't equilibrate anymore at any given finite time scale, and you are crossing from one class to another. It's a very subtle difference, right? Okay, you're crossing from class 3 to class 1. But these are different structures. I mean, measured by the fluctuations at large length scales, these are different phenomena. Yes, it is very subtle, and people might say, fine, I mean, your exponent jumps from one to another, but still, these are different phenomena. Well, and the first bar, I'm not going to talk about it, it's the onset. It's the onset of the, that's where, okay, so what is TO? It's the onset of the supercooled regime, where, so here we measure basically the energy fluctuations, okay? We measure the covariance in the energy of a set of the energies at one temperature and correlated with the next temperature, 2 subsequent temperatures. What that means is basically here they are uncorrelated, so the system can, in this region above T0, the system can still equilibrate, but once you enter the region below T0, you are entering basically in meta basin of the landscape. So you get stuck in certain energy minima. And yeah, so you will never get out of it at finite times. And unless you do, even swapping particles is not enough. So yeah, so that's the onset of the supercooled regime. And we see that even, so the entropy I mentioned in the very beginning, it has also some changes in these 2 temperature regions. So it shows some characteristics, these shoulders, they just occur at these 2 characteristic temperatures.
What means the structural entropy?
What it is?
Yes.
It's the S2, what people call S2, structural entropy based on the G of R. But in this case, it's based on the S of K. It's the one I showed in the very beginning.
Okay.
It's a functional of the structure factor or functional of the G of R.
Yeah.
What that means is basically you're measuring entropy based on your pair correlation functions.
Okay.
Without any orientational, I mean just, why is it easy to measure? Because we have the structure factors we just plug in. That's the entropy. Well, in fact, this is the structural entropy difference, excess entropy. This is the difference to ideal gas.
Okay.
Yeah. So in the limit of T infinity, it goes to 0. So the ideal gas has the same entropy as the system with infinite T. Well, ideal gas. Yeah. And so here's also a very interesting phenomena, and then I will stop. So we use different cooling rates. We cool very abruptly, we cool slowly, we cool more slowly. The structure factor doesn't change at all, except at one point, which I'm not showing you, at the very small k. What happens is that the large scale correlations, the structure factor changes only there for very small k, for very long length scales, basically, large length scales. Everything else stays the same. And I believe this is not the case in ordinary glasses. If you use different cooling rates, you get different local structures. That also depends on the glass models. But here, the long-range interactions basically cause we believe, a quick communication between all particles, and the system doesn't care much about the cooling rate. And that's another message, take-home message. Maybe 2 more minutes.
Yeah, thank you, Tom.
All right, I'm now going to show you some differences mechanical differences between our glasses and, for instance, Leonard Jones glasses, conventional glasses. Okay, so you can measure the softness, vibrality, measured by. So what we do here is we write down the Hessian, the dynamical matrix, and the lambdas are omegas, the frequencies, the eigenvalues, and the eigenvectors are e's. And if you sum up over all modes, you get the so-called vibrality, which is given here in the color bar. The higher vibralities are the so-called soft spots in glasses. Soft spots because they are more susceptible, they are more prone to external, like for example, when you thermally excite the system, the glasses will start fluctuating here in this spot more, rearranging more. Here the rearrangements will be higher than in the blue zones. Now if you look at the hyperuniform glass, our glass, it looks quite, fantastically different, I would say. These soft spots are highly localized, point-wise, unlike in conventional glasses. And this actually leads to the fact that, I'm making it short, the non-affine displacement, which is you have a glass, you shear it, you get this, you let it relax, you get this, you distract these two, you get the non-affine part. This non-affine part is at least 1 order of magnitude smaller in our glasses than in conventional glasses. So this is the displacement field. Usually I ask which one is which one, but let's skip that. So the hyperuniform glass is less coherent than conventional glass. If you excite the conventional glass, if you shear or whatever, the particles will display along these arrows more coherently. Whereas in hyperuniform glasses, it looks like more brittle. And so that's what I was mentioning. The non-affinity in hyperuniform glasses are an order of magnitude smaller. They are more affine. It's almost like a crystal. Well, in a crystal it's 0, but we are getting there. And this is the shear modulus, the non-affine part of it. It's also smaller. It's a novel type of a glass, if you want. However, some other colleagues published just a few months ago in a high-impact journal something about this, but they have a completely different model. So this part is kind of gone, unfortunately, but we can still sell this somehow. They have a hard disk model. It's a very nice study. They don't use long-range interactions, but they do optimization so much that they get these values also very low, and they get also glasses that have these different distinct properties from conventional glasses. Okay, with that, I would like to thank you for your attention, and sorry for overstretching a bit.
Don't worry.
Thank you. So this second part is under current investigation. The first part has been published here, and unfortunately the mechanical part has been already published in a different model. But, okay, sometimes it is like that.
Do you have any questions?
Yes, I have 2 questions.
Please.
I'm a thermodynamicist, so I ask you about the thermodynamics.
Please.
You have the liquid, it's a thermodynamic phase.
Yeah.
And when you get to the melting temperature, it becomes supercooled.
Yeah.
And the supercooled is terrible out from equilibrium.
Yes.
It's a non-equilibrium. And then you supercool it and you get to TG, where the TG depends, as you said, on the
Simulation
rate.
time, yeah.
But the physical feature is the viscosity.
Yes.
You showed that in TG,
Yes.
the relaxation time is 100 seconds, but that corresponds to a viscosity of 10 to the 13th quasi.
Probably, yeah. I didn't show seconds, but I showed that it.
Well,
the relation, it diverges. Yeah.
Ah,
Yeah.
so I was saying you have also different kinds of regimes.
Yeah.
Thermodynamically speaking, the liquid is non-equilibrium, but if you have an unset, you set a temperature T0,
Yes.
so TC, you have two different kind of relaxation processes. You
Yeah.
have the slow ones,
Yeah.
and then you have the large one, the beta,
Yeah.
and that's why you have the difference. So,
Yes.
do
Yes.
you take in consideration the structure? That structure is of the supercool liquid.
Yes. The entire structure. Okay. So.
Well, I'm talking about the supercool liquid.
Yeah. Just a second, please. So. Okay. So these are different. By the way, different relaxations depending on
Yes,
different
yes, for
different
example,
modes.
You have TG, you have
T-
100, 10 to the 2. That corresponds to
yes.
a physical number.
Yeah, but this is extracted from that. I don't honestly know what that means in seconds. So.
Well, that's strange because it's in seconds. The relaxation time in TG
Yeah.
is 100 seconds. That's why.
Is it?
Yes.
Okay.
And it corresponds to a viscosity of 10 to the 13 watts. And
Okay.
what do you have
Yeah.
physically are two kinds of relaxations, the alpha and the beta. So more or less, I am trying to
Yeah,
see the
no.
thermodynamics if
Yes.
it is more
When I check the intermediate scattering function, there is an alpha and there is a beta relaxation.
Yeah.
Yes. But there are a couple of nice works also in 2D. These alpha beta relaxations are not very clearly separated from each other like in 3D. My alpha beta relaxation looks more like so this is Lin log plot. You would have something like this, right? You would expect
Yeah,
alpha beta.
because the alpha, the change is slower
Yeah.
than the beta one.
Yes.
As you said, it goes more quickly.
Yes, but in these glasses with long-range interactions, something weird happens which we don't understand. This goes like this, and there is a very small beta relaxation, alpha relaxation over there. So this we don't understand yet. It's a good question. So that also creates a bit complication how to define alpha the T alpha. I'm using the classical technique. I say, okay, if it's 1 over E, then this is my alpha relaxation. But the scattering function itself is not as clean as in 3D. So that gives a complication of definition of the tau alpha. But back to your question. So at the onset temperature, when you go into a supercooled regime, you don't relaxate. You don't equilibrate anymore.
I know you don't.
So yeah, so what I'm doing is actually I'm taking the global structure and calculating the structure factor of the global structure, even though I'm in a meta basin probably somewhere. And so that's all I do. I don't know if
Yes, and,
so.
and one other question.
Yeah.
How do you define the excess entropy? It was
Classically, it's defined over. This is actually what people call S2, the excess entropy based on the 2-point correlation function G of R.
But
Per
does it have any sense thermodynamically?
yes.
Because there's an excess entropy that might be defined between the entropy of
Yes.
the supercool liquid
Ah,
and the
no.
entropy of the crystal.
Okay, that's a good point.
Well, that's why.
This
yes.
is something we don't do, but that's something we could take into. Yeah, that's maybe a good point to also calculate this, as you say,
Yes,
and then you would have a
because
different.
It cannot go
Yeah.
to 0 because of the third law, and then
Right.
you have thermodynamically you may
Right.
define a temperature.
I agree. I couldn't agree more. But what we do here is we define the excess entropy between what we have and the ideal gas.
Oh, okay.
That's because it works very well for high mean field. So these conditions have been worked out many decades ago. This is it's called also random phase approximation, I think, if I'm not mistaken. This is works better, increasingly better as your correlations are increasingly less important. That means at mean at high temperatures. And then at higher temperatures, what interests us is the difference, the excess in relation to the ideal gas. So that's the excess entropy between ideal gas and a state at any given temperature T, very simply measured by the structure factor, okay? By this form, not really taking into account 3-body or 4-body whatsoever correlations. So, but this does a good job because these guys later on worked on continuation of this, even in active Brownian particle systems, etc. They can, this excess entropy can tell you, that can give you the phase transition. Even at lower temperatures, surprisingly good. Because what they also did later is that they took into account larger larger expansion modes, not only to the. So when they derive this is only to the first or second expansion term, but you can do it more, and then it gets increasingly better at even lower temperatures. But it cannot get there where the physics are interesting for glass because it is out of equilibrium. You don't equilibrate anymore, and this only works actually for equilibrium. Yeah, so maybe that's something we could also think about using with. Thank you. It's
First of all, thank you for your talk and
a pleasure
for your results.
Thank you.
One question that I have is, how did you notice that you have to put these fluctuations in the amplitude of the potential?
Okay, so I can show you my motivation experimentally. But then it happens that the experimental group doesn't work on it anymore, and okay. No, wait. So these guys in Potsdam in Germany used to work on that system where you have these gold-coated nanoparticle, but it's porous. And then there are cis and trans molecules in the solution. They put light, they shed light on it, so that it's pressure. This pressure. So these red worms have two metastable states, either this or this, L shape or string shape. When you put pressure, when you switch on light, what happens is, I think they go from one to another, I can't remember now exactly, and they start penetrating the sphere, the gold nanoparticle. And then this creates, then there's a chemical reaction going on. It is like a constant in and out. So this creates a density field which is higher around the particle of these cis and trans molecules than outside. So there's a density gradient which creates diffusophoresis, which means basically these particles, so you push out the flow in order to regularize the density, homogenize the density of these molecules. But we know that in 2D, due to the Stokes, if you have got incompressible fluids, the colloid generated flow, it's like a flow monopole if you want, okay? This creates like flow field, pushes the flow outside, okay? We know that this flow field has to be 1 over r in 2D. Otherwise, you cannot solve the Stokes equation for strictly 2D. In 1D, in 3D, it's 1 over r squared. And if we have a quasi 2D, we expect something between 1 over r and 1 over r squared. Isn't that what we have in our model? That's exactly what we have in our model. Now comes where the pole dispersity comes in. You look at this picture, you see particles of different sizes. Particles of different sizes means a different strength to push the colloids. Now that's not exactly my model, because that would be my model if I take Vi and Vj. So each particle has a different amplitude to push the flow. But if I take this, I have a problem in the simulations that they cluster together those that are, so that you get this polycrystalline, you don't get a class. So, but the motivation to take interaction polydispersity comes from these experiments. And actually, look what happens when you switch on light. It's a soft glass if you want.
Okay.
But unfortunately, they don't have this setup anymore. They're not working on it anymore, I think. So this is, okay, so I've got to say, so I moved to China 4 years ago as a faculty, junior faculty. Before that, when I was postdoc, there was a colleague who was looking at these movies from he was also a postdoc with me, but he just finished his PhD and came to our group, to the neighbor group. And then I saw this video on his computer. I was looking over his shoulder. I said, "Hey, what is this? This must be hyperuniform." He said, "What is hyperuniformity?" I said, "Okay, let's talk." And then actually it turns out this is nearly hyperuniform, not perfectly, but nearly. But what I'm saying is this is more than 8 years. So, and then I finished my first project as a postdoc, then I moved as a faculty, and I stopped working on it for a long time. So now I'm coming back to it. So unfortunately, these experiments are not available anymore. That's why I'm looking actually here for new experiments.
But this is also very related to the active matter thing, right? When you use the light into...
This is, yes. I call this actually, well, these constituents are not active on their own, but it's like an activated system, if you want, because you pressure, you put a pressure, like you inject energy in principle. So yeah. But they themselves is not active on their own.
Yeah,
it's like,
you also mentioned the active matter thing.
Yes, yes.
So I think
Yes.
it could be related.
I see. No. So there are different mechanisms for active systems to get hyperuniformity. It is related in that sense that these is also activated systems, but the mechanism is different here and there. This is nearly hyperuniform. It's very interesting, but it's more than 8 years, so we don't have the experiments anymore. Sometimes you got to be quick. But yeah.
Here is another question.
Yeah, first
Okay.
of all, thank you for the talk. It's very
My
nice
pleasure.
and interesting. Now, for my question, can we go back to the pictures of the structure factors for power law interactions?
You can go back anywhere, anytime.
Attention precisely.
These ones?
A little bit, it's like 9 slide.
9. Number 9?
10 or something like that.
Oh, you mean the first part?
Yeah. So
These ones?
yes.
Yes.
Yeah, that's precisely. That's kind of,
Yeah.
For the pictures of the structure factor, what kind of physical systems are trying to modeling to this picture? Because
Systems with long-range interactions. For instance,
for the exact values of
The-
for these
okay.
exact values, because I
it's not, okay, I'm not trying to, okay, these exact values are chosen randomly in order to get values below and above. So let me go back. So in 2D, d equal 2. So this is S, okay? So here is non-hyperuniform. Here is hyperuniform, just like here. And here is the difference by 1. So I'm trying to mimic our findings for values below and above 1. Now, which real systems can correspond to this? Okay, so if you have 1 over R, you have a Coulomb system. Okay. If you have 1 over R, 1 point something, this is more like the experiment I showed you. Because in this experiment, because it is, if you have 2D system, it is 1 over R. If you have 3D system, it is 1 over R cubed, the flow generated. But what we have here is, in the experiments, there's a substrate, there are colloids on it, but it's open. So it is quasi, there are also convections, flows. In this system, what they do is they measure the force of a single particle, and they find a value close to 1.5. So this coordinate system in quasi 2D could be this. This one, I don't know.
Yeah, that was my question, because I wasn't up if this kind of pictures correspond to some kind of physical system, or it's just like a random chosen for plotting or
Random. So long-range interactions are important. They are everywhere in nature. Some of them are even here in colloidal systems, such as this. This is just to show that there is a distinct behavior below and above one. And you know, I'm sure you can come up with some models. I mean, there's this Riese gases, R-I-E-S-Z. That's a huge field, and there are many people working on it, many smart people. They take also arbitrary exponents.
Yeah.
If you are looking for a physical system for this, I don't know.
Okay, yeah.
Yeah.
Thank you.
Question from this. Yes, yes, yes. You.
There's no microphone.
Okay.
Sorry.
It's very true for a system in Mexico and then National University. We have a question for
Thank you.
what the experience in the apprenticeship for the scientific connaissances in the very perspectives internationals for the uncountable countries and
I sorry, can you repeat the question? I didn't get.
okay.
What are the perspectives?
What is your experience for the
My experience.
yes,
My personal
yes,
experience.
yes,
Yes.
the spirit
Yes.
and working scientifics
Yes.
The different countries.
in the world,
Oh.
in a country,
Yes.
in the world.
Yes.
What is the experience scientifics and with a perspective and we curiosity, personal curiosity.
Yes.
For a perspective
That's
in
very
the
important,
connaissance scientifics in Occidental cultures and Oriental cultures, Oriental cultures in Chinese.
Well, so first of all, I can. It's a difficult question, but I can certainly recommend, highly recommend, to based on the opportunities and possibilities to go abroad, to experience different cultures. Absolutely a must, especially if you are in academia, because it's not only about everyday culture and life; it's about scientific cultures. So how people approach scientific questions. Of course, the core is the same everywhere. Physics is physics, right? Formulas are formulas. Like if you are in China or in the US or in Europe, we are working on problems that have the same universal laws dictated by physics, right? So there is no difference in the content of what you are doing. But for example, there are differences in working groups. When I was in the US, for example, my professor was a super busy guy, and he had a small group, and he was
Torquato.
Torquato, yeah. He's a highly respected man, and he would have meetings once a week with his students, for example. Whereas in other places, for instance, in Germany, I only saw my supervisor whenever I had a result. So there are different working cultures, and I'm not saying which is better or which is worse. I'm just saying there are differences, and you have to figure out the best one for you. So in some places, for example, people work hard in the sense they spend a lot of time in the lab. In other places, they don't do. They appreciate more. For instance, in Europe, weekend is weekend, okay? You don't work in the weekend. When I was in Paris, let me tell you an anecdote. Because I met my collaborator, we had to finish a paper. We wanted to work on a Saturday. They said, no, you're not allowed to go to the institute. It's closed. You cannot go on a Saturday. I said, okay, fine, then we will go in a cafe, work in a cafe, right? We sit together in a cafe, we open our laptops. The cafe owner comes, no, you cannot work in the weekend. I said, what the? Okay, then we find a Starbucks, American. We had a coffee, we stayed there 3 hours, we worked. So there are different approaches to working in different countries. And of course, also the everyday culture life can be different. But
So
if you travel enough, you see.
You say that there is the working way and the efficient way.
Yes. In the US and in China, they are actually very similar to each other in some senses, respect. People spend a lot of time in front of the computer in China. They work also a lot, like in the US, as I said. For instance, that's a difference in working culture. But of course, it doesn't matter if you do physics, if you do law, if you work in, you know.
And the perspective educative is very different?
It can be different. It depends which group you work in. It is very personal, individual. So, for instance, according to recent surveys, PhD students in China spend less time with their supervisors than in Europe. Even though the outcome is more somehow in China. It depends where you are, but for instance, Chinese institutions, as you know, are, you know, some of the top world's top universities. But again, if you go to a group, for instance, people around myself, I know that their students are happy usually. So it depends where you go. But from the educative perspective, if you do something related to life sciences, you will learn the same, no matter where you go. Maybe you will in place A you will learn it faster than in place B, or vice versa. But in principle, you know.
In a finished question,
yeah.
Is what is the with welcome to the collaborators in the two installations for UNAM in Berlin and Peking for the community original the countries.
So you mean in Berlin, in Germany, and in China there are UNAM facilities?
Yes, and facility and
like an office. Maybe you can ask in Spanish if no.
Yes, also my English.
No problem. If you don't remember the word, you.
Okay, voy a decirlo más en español. ¿Cómo ha sido la bienvenida por parte de los alumnos de los países en donde tienen las instalaciones que usted ha tenido la experiencia tanto en Beijing?
So,
China,
how was the welcome from the part of the students
Yeah.
in the different countries where you were living and working?
Welcome for students?
Yes,
like,
when you arrived as a professor, how was the welcome from the students?
Okay, so I work in a research institute. It's not a university, so we don't have many students. We don't have undergraduates. We have PhD students, and
it was always like that. In Princeton, you didn't.
No, in Princeton. Okay, so
in China, definitely not. But in Tel Aviv, in Princeton,
also in China there were students, but there was not a specific welcome.
As many. So it's not a university, but
yeah.
in Tel Aviv or Princeton.
But what's the question exactly?
So
like,
you I think that is thinking that you give a course and how it was if you did a course for a lecture.
I see. Okay. So how the students actually perceive.
Yeah, exactly.
Okay. So. Well, I did, in Princeton, I didn't give classes, but in Germany and in Tel Aviv, I have replaced my professor many times. I would say, so in Tel Aviv, people are more direct. If they don't understand, they straight ask you, or they say, it doesn't make sense, what do you mean? In Germany, they are more polite. But overall, I would say it was a good experience. It was a good experience because if the student is interested, they will show their interest. You see? So how they show their interest can be very direct or very polite. It doesn't matter. I don't mind. But as long as they show their interest and welcome you, and that happens everywhere in the world so far, I experienced, it was very nice. As long as they are interested, you will be always welcome. Yeah, but I didn't give classes in China. I don't know, but I know that students we work with, the PhD students, we don't have undergraduate, but the PhD students are, they are also quite so there's a threshold to approach you. They don't come and say, "Hey, professor, I don't understand this and that." So it takes a bit more time that the students approaches you in East Asia. Yeah.
Thanks.
You're welcome.
Yeah,
I hope I could.
Okay, maybe
Yeah.
last question.
Yes, I have a little one.
Yeah.
Why do you say that there is no symmetry breaking in this phase transition?
Well, yes and no. There's no symmetry breaking, but also there is no real phase transition.
because I think that there can be interpreted the different classes of,
Yeah.
of
Hyperuniformity, see?
like symmetry breaking, isn't it?
No, I don't.
No?
Not sure.
I don't know. I mean, it's a different degree of suppression, different way of suppression of density fluctuations, different classes. But it's.
But also it's a different structure, isn't it?
It is a different structure, but they are both disordered, at least by 2-point correlations.
Yeah. But,
So
but maybe it's like a more complex.
maybe if you go to higher order correlations or
Yeah,
whatever,
so
it could be.
something.
Could be.
Because
Yeah.
you plotted like order parameters that
Yeah.
are
Yeah,
floating.
Yeah, exactly.
you're really before you're coding, you're always making a UV, like kind of UV cut. You're making a cut.
Cut where?
Just like kind of.
You mean the cut where?
What cut?
What cut?
Critical
Before,
point.
no, before you had an integral in the slide.
Ah.
Yeah, you're
The cutoff, you mean?
you upper the cut. You made a upper cut. No.
But that is only for the
Yeah.
entropy, from 0 to. So this k value, if this k this in principle has to go to infinity, but you can't do this if you have an S larger than d half, for example, 1.5.
Something similar to techniques of renormalization group, no?
Yes, actually,
And it got my
yes.
you said that there's not exactly a phase transition, so how can you apply that kind of techniques?
But that's a different problem. This is the liquid case.
Yeah.
There's no phase transition. That's high temperature.
Okay.
So we don't apply this technique to glasses. Well, not yet. Maybe we will. But what did we do with the glasses so far is basically simulations. This theory applies for high temperature liquids. We are regularizing this integral by introducing this cutoff. So that we can actually tell that, we can compute and then tell, oh, that's the difference to what it should be. So yeah. So we don't do renormalization theory or and not even the simple theory for the glasses, because it doesn't work there anymore.
Okay, so it's really more complicated than I thought.
It is. Especially this part is quite subtle and quite technical. All I want to say here is, can you, this slide, 14, one more, yeah. Thank you. All I want to say is here, if you choose two different S's, somewhere in your system there's a thermodynamic parameter or something that behaves differently, and we figured out this. We saw first that the entropy is behaving differently, and okay, what can we do with the entropy? We said, okay, specific heat capacity depends on entropy. Let's look at heat capacity. Okay, what can I do with heat capacity, which I can also measure in experiment and in simulations, is potential energy fluctuations, and then they behave differently. So if you are here in between, you are more sensitive to cutoff, basically to the cutoff in the to fluctuations, correlations. Yeah.
Okay. Before everybody goes and we stay talking alone, let's thanks to
Thank
the
you.
speaker.
Thank you.
Thank you very much.